Hi DEFCON. How many of you have ever used a vending machine? Who has ever wanted to hack them? Alright, so this talk is for you. So, just to introduce myself, I'm a security engineer, I'm from Switzerland, so no, I don't speak Swedish. I don't know, but many Americans think we speak Swedish in Switzerland, but no. I speak French, so excuse my English. I also do a lot of CTFs. I love old video games. I brew and I love beer. And as I said, I'm a noob speaker, so if you have any comments, it will be greatly appreciated. So, how did I get there? First, some years ago, I created a MAME cab, so it's basically an arcade machine with a laptop inside, and I play video games using emulators with this. And to be more realistic, or to take money from my friends that came to play at home, I searched and I bought a coin acceptor on an auction site, and this is the tale of what I did with this. So first of all, any kind of machines that accept coins or bills are used every day, especially I think in casinos or in Vegas, like ATMs, vending machines, slot machines, etc. And there are multiple devices that are used to process money and give money back. For instance, coin and bill acceptors that are obviously used to count coins and bills can also detect if you insert a false coin or a coin from another country, etc., etc. And it uses different methods to recognize the money for the weight, for the size, even visually. And there are many ways to recognize that, and it's used to send, if the coin has been accepted, to the mainboard, and the mainboard needs to process the events that a coin has been inserted, and it's the machine that processes that you have entered, for instance, $1 or etc. Other devices are coin hoppers that is used to give money back, so when you need to get the change. So it's pretty much like a big tray that operates using some commands and gives you the money coin by coin back. So if you need to receive back like $1 and this tray contains quarters, the mainboard will send a command to release 4 coins so you can get your change back. All of this stuff communicate with several protocols. They are parallel, serial, another protocol is MDB, and the last one is ccTalk. All these protocols are very vendor specific. So one vendor can do normally only ccTalk or only serial devices, so you need to check whether you get the right protocol you want to use. So since I didn't know about this, I just received my coin acceptor, and it was ccTalk, and this is what we will be talking about. So ccTalk is a name for coin control stock. It's a semi-proprietary protocol maintained by a company in England called Money Controls. Semi-proprietary because the specs are available on ccTalk.org, but some parts of the specs are only available after signing an NDA. So you just have parts of the information, but not everything. So you have to find something and check this. How does it work? It's simply a request and response protocol. So just send a request, the device sends you a response, and that's it. It uses an UART data transmission, so it's pretty much like a serial communication at 0.6K, 8 and 1 on TTL signals. And each device is on a bus, and it has its own address. For instance, 1 is the controller, 2 is the coin acceptor, 4T is a coin hopper, etc., etc. So on the same bus you have all the devices that can communicate between each other. A ccTalk frame looks just like this. So you have 1 byte for the destination address, 1 byte for the data length, 1 byte for the source, 1 byte for the header. I'll talk about this later. Several bytes of data. It depends on what command you will send to the device. And a checksum. The header is the command that you will send to a device, and if the header is equal to 0, it means it's a response. So you don't actually have a response to what. So you need to know what you asked to get the correct answer. The checksum is a simple checksum. It's just the complement to 255 of the whole packet. So all of these headers are commands, as I said, and from the documentation you can find, you have the list of all the headers, and you have, for instance, all the headers and the corresponding commands. And if you get in the documentation, you have all the data you need to send when sending a request, and all the data that comes back, so you can actually see or understand what's going on the bus. For instance, you have here a sample command that is sent. You can see that it's a sample poll, so it's kind of like a ping for a device on the bus that is sent from the address 1, so it's normally the main board, to a device at address number 2, normally a coin acceptor. And if you send this, you will probably see a packet like this on the same bus, which is a response, 0, to what? We don't know, from device at address 2 to device at address 1. So, just by looking at those packets, at the response, you cannot know exactly a response to what it is. You have to sniff the bus all with the request to actually see the response and know exactly what it is. The second packet here is header number F6 in X, which is request manufacturer ID. And in the response, you have NRI, it's the manufacturer of the device I bought. So, I've been able to ping this device to know some information about this. Now, I wanted to actually know if there was a coin entered, if it was correct, if it was 1 Swiss francs, 2 Swiss francs, etc. So in the documentation you have a header number 229 that you just send to a coin acceptor, and you receive back 11 bytes. The first byte is the counter, and you have 5 groups of 2 bytes as a result. The counter is actually every time the device has a new event, like you inserted a coin, the coin was accepted, was refused, etc. This counter is incremented. So for the main board, you have to actually know which was the state of the counter, and if there's an increment, you know that there was a new information and you have to pass it. The results are sent in 2 bytes, as I said. Normally the first result contains what is called the validation channel. On coin acceptors, you have what is called validation channels. It's normally 16 ways or kind of coins it can recognize. So you can make the device learn 16 different coins. And each one of these is assigned an ID, and it's that ID that is sent in the response. So there's a nice trick there, because since you only have the ID, the coin acceptor only knows an ID. It doesn't know which kind of piece of coin or its value. It only knows an ID. And the main board needs to correlate the ID with the actual value of the coin that has been inserted. We'll check that after. The second byte contains the error code, so if it's a bad coin, if there was an error recognizing the coin, or if the coin was accepted. The problem is that all these codes are vendor specific, so if you buy different kind of coin acceptors, there won't be the same error codes or error IDs, etc. And even sometimes the 2 bytes are swapped. So you really need to have the documentation, or you will have lots of trouble when doing this. So for my initial project, I implemented the ccTalk protocol on a TINC, a small TINC device, and it simply polls a coin acceptor sometimes, and as soon as there is a new coin inserted, it will send a keystrokes to MAME, the emulator, to actually insert the credits in the game. So here you have the board. There's a bus pirate there behind. That's because it was only for debug. You have the TINC right here, the coin acceptor there. And if I put some money, the game will see that there are new credits. If I put 2 Swiss francs, there are 2 new credits just there. Etc. So that way I had the first part of my first project was nearly done, so I was able to put it in my main cab. It was working, but I was telling me, can we do maybe more, because that's a simple project. It only uses the coin acceptor I bought, etc. And there are many other machines that use those kind of protocols, etc. But the problem is that it's difficult to track those responses. You cannot see them because the header is always equal to 0, and you don't know which answer is to which request. And I didn't find any open source sniffer for ccTalk. So I created 2 tools, which are called ccSniff and ccParse, that are used to sniff data on a ccTalk bus, and the other one is used to actually parse the data you sniffed in a way that you can pretty easily understand and learn exactly what happens on the bus. If you want to have a look, can everyone see correctly? Yeah? All right. Sorry? Cannot do many anymore. Maybe if I do this, it's a little bit bigger. Maybe you'll see better. I cannot, sorry. Well, so you have on the upper side the packets, all the packets list that you can select. And when you select a packet, you can see on the bottom, the header, the corresponding function directly, so you don't need to check on a table, etc. You have the row dump of the packet. And if you take some other packets, like the one I showed you before, the request manufacturer ID, when you check the response, you have an automatic payload decoding. And it's the same for nearly all of the ccTalk packets and responses. Again, if you check the read buffered credits and error codes, so the one used.
Hi, everybody. You know the drill. Can I have a lucky audience member volunteer? Come on. You, sir. Oh, I just meant you get to watch us. I'm here. We have been doing this all day. Yes, sir.
Thank you.
All right. Oh, is it your first DEFCON?
No, sir.
God. Oh. All right. Anyway. Cheers.
Cheers.
Cheers!
Yeah, don't worry. We'll see you tomorrow. Say what in Swedish?
I don't know.
I'm going to go before I have to figure that out.
Okay, where were I? All right, so yeah, okay. So as I said, this is read buffered credits. So I pulled the coin acceptor to actually get me the data, the status, and I have all the details, the event counter, which is 0 because it was starting, and all the results that are 0. But with this tool, you can pretty much get any information about what happens and what is happening on the ccTalk bus. That's cool, but okay, so now I can read on the bus, but yeah, why not write directly on the same bus? Like, for example, telling the mainboard, like, hey, okay, I'm the coin acceptor, I received a new coin, and now a new coin, and now another new coin. That's new. That could be pretty great. Oh God, sorry. All right, so you see the point. The problem is that you only have one wire for the whole bus. So if as an attacker you will receive the requests, the device also receives the same requests and responds directly. So if we try to respond just before him or just after him, it won't work. We have many chances that we will jam the signal and make things quite worse. Fortunately, somewhere deep in the documentation, we have what is called multi-drop commands, which is normally used by the control to solve addressing conflicts. Like if you have 2 or 3 coin acceptors, you can set them different addresses, and it's simply just a command that you use header 251 address change, and you give as a parameter the new address to the device. So you just send that packet, and the device will say, okay, fine, now my new address is the one you sent. And what is great is there is absolutely no checks made on the device or on the mainboard that I tested. So you can just connect to the bus and just send one little packet to tell the device to change its address, and then you get its address. If I show this, you have the mainboard there, which is address 1, the device at address 2. It sends credit read, it sends credit responses, etc. I just get on the bus, like I take the address like 77 and just send a packet address change to the device. It will tell the address 99, for example, and I take the address 2, and the mainboard will continue to ask me, instead of the coin acceptor, my status. And that way I can respond, okay, hey, I got a new coin. I got a new coin too. Again. That's pretty great. But since it's on one wire, you have to be really careful about the timing, because if you write something, if the device, another device was also writing on the same bus, it will collide. And normally the bus will stop, the machine will reset, or there will even be, I could test it, an alarm ringing on the machine, and you have to run quickly. I won't say more. So you really have to check for the silence, and in the specs it's indicated that the device needs to be polled every 200 milliseconds. So as the packet needs about 8 milliseconds to be sent, there's normally enough time for us to do. So the thing is, to sum it up, to hijack a device on the bus, you have to scan this bus to search for a silence period, prepare the injection, create the address change packet, wait for the silence, just send this packet in your silence window, and then directly take the address of the device you want to hijack and start respond instead of it. And when you're finished, that's also pretty cool to just set the address back so the device is at its old address and you can just leave and everything works. And again, you need to do this while the bus is in use. It's quite complicated. So I created a tool called ccJack, which automates the hijacking process. It can emulate a device, so it scans the bus, it reads every packet that passes on the bus, and each packet which is directed to the device you want to hijack, he will record the request and the response. So as soon as he will take over or hijack the device, he will start responding by the last response the actual real device used to send. So normally it will be pretty much transparent, so the mainboard won't fire an alarm or something like this. It also uses a bus pirate to sniff and inject. And one of the coolest examples I have is to inject coins. So as soon as the coin acceptor is hijacked, just start incrementing the counter. As I said, the counter is whenever there is a new event. So just put one coin. If it's accepted, that's okay. Hijack the device and start incrementing the counter, and you will see that there is a new event that is the old one, that is a new coin has been inserted, etc., etc. Another thing that I use also on the same machine is that if there is a glitch, like if the counter value is lower than the one that is set on the main board, there will also be an alarm, and again you have to run quickly. So as a demo, sorry? Maybe after, I don't know. That's up to you. I'm sorry, I wanted to do a live demo, but my coin acceptor just crashed in the speaker room like 20 minutes before, so I only got this loosey video. I hope you will understand it. So what do we have here is a shell, obviously, and here it's the MAME emulator that I will use to actually show you what happens. So the tool ccJack needs several arguments. You give it the interface, so the bus pirate, the source address of the device to hijack, the destination, so the address you want to send the device to, and a time to sniff the packet, so it will listen, like I said, it will listen to all the responses, etc., and record the new events. I just inserted 2 Swiss francs, so I have 2 credits now. And if I send this, I will change the address of the device at address 2, so the coin acceptor, I will send it to address number 7. It's sent. So now the device, the actual device is on address number 7, and I took its place and respond at its place to the main board. If I look at the values, I see that I have actually learned an answer to request 229, so the request the coin acceptor status, and the response is for here it's 01 is the counter, 07 is the coin ID, and 01 is that there was actually a new coin accepted. So now what I will do is change the address. Let's say header 221. I will add two new coins. So I will change the payload. And now I will have 2 new credits. Great. And what I found also is, if I do that again, that will work. And normally in the specs, if the counter increments too much, like there are, if it increments in 10 to 10, normally it only needs to get the last 5 results, the ones that are actually in the response. But as I found in several machines that I tested, is that you can just put whatever value, it will just check the last response code. So let's put FF as the counter value, so we increment by 200, and what happens? Yeah?
Counter decrease when you use credits? So in your video game example, you play a game, does the counter on the motherboard decrease?
No. It's afterwards. It's another counter that is in the main board. That's only a counter for the coin acceptor. That's it. All right. So since it's nearly over, we'll get to it more quickly. So as the acceptor is offline, so we have hijacked it. So we are able to just send commands to it. So we can change the validation path. So we can just say the path normally that is allowed for the $1 coins that exists, right? Yeah. Okay. So you just tell the coin acceptor to change to learn a new coin. And you set the validation path of the $1, and you just put several quarters or cents, etc. And it will learn this new coin, and when you actually put this new coin, it will send the ID of the $1 and the main board will trade it as $1. So it works. That's great. The other thing that is great is you have several paths for the money. Like when the coin is not accepted, normally it will give it back to you, so you can try it several times before dropping the coin. And you can also change that. So just invert the two, so when the coin is not recognized, it will get in the machine, and if the coin is accepted, it will get it back to you. So as soon as you win, you just play again. That's great. There are many possibilities, and again, there are absolutely nothing, no authentication, nothing. You just have to be connected on the bus. Regarding protection and security, there are several things. You can provide a PIN code on the device. The only problem is that the PIN code needs to be sent in clear text to actually be used. So just sniff the bus, check for header 218, that is provide PIN code to a device, and just read the four digits that are inside, and that's it. You can help by just pulling the power cord and boot back the machine, and it will actually send the PIN code. So yeah, it's of no use. There are also encryption. I didn't actually put a lot of time on this, but there are two encryption methods that are used. It's one is proprietary. It's a 24-bit key. The other one is a DES encryption, and they use a pre-shared key between the controller and the device, so you can put it. But the problem is that it's a different header, so you still can request the device using the unencrypted headers, and while the machine is in use with the encrypted one. So why not? I just added that yesterday. I was working in the Caesars, and there was an open machine. So just to show you exactly where. You can see that. You see here, the machine is just open here, and the bill acceptor is just right here. I don't know if it's a ccTalk one. I didn't test it. I wanted to be there and not in jail or something. So, so it's just there. The connector is just there, so you just can create or put you in on the wire. Normally, it's the fourth one. It should be that red one there, but I'm not sure. So yeah, normally these machines, if they use the ccTalk bus, you can just get into them something there. All right, other things, I will get quickly, sorry. Other things that might be good points of research is the encryption support. There are many things that I think you can do there, because 24 bits is a bit weak. You can also dump the internal memory of devices. You can upload a new firmware on the devices, so you can do pretty much you can do many things with those, and that's just the start. So in conclusions, the specific protocols are quite fun to analyze. It's quite easy. You can find really fun things to do with this. You definitely need to look more in depth in ccTalk, because since it's money-related information, you have interesting applications, right? And just get a bus pirate. It's a fantastic tool for hardware hacking and pretty much all stuff. All the tools are available on my GitHub account, and I will post several articles after DEFCON on my website, balda.ch. And that's it. Many thanks.